Hi everyone, my name is Carmelo Cascone. I'm a technical lead at ONF, where I'm responsible for Dataplane development using P4. Today, I'm pleased to welcome Chris and Ankur from Keysight Technologies. Chris is a software architect working on emerging technologies. He's also an active contributor to many P4 working groups. Ankur is a director of engineering in the product strategy group, leading the network test virtualization products. They both have extensive experience in the networking space, and they have helped develop the well-known Ixia line of packet testers. Today, Chris and Ankur will demonstrate Snappi, a new framework for line rate testing based on the Open Traffic Generator API. Snappi has an ambitious goal of replacing a well-known library for packet testing in the P4 community, which is Scapy, used by many developers today, including myself. So welcome, Chris and Ankur. Please take it away.
Thanks a lot, Carmelo. It's really fun to be here at another workshop. And today we're going to introduce a new framework, a new workflow, some exciting new tools that are available for download immediately. And we hope we can further enable the P4 community to do data plane testing. So let's take a look at the landscape today for packet testing with any kind of data plane, and in particular P4. Down here at the lower end of the speed scale, we do simulation on a PC, and we run our behavioral model or maybe a Tofino model or some other data plane, even Open vSwitch or whatever you use. And we throw packets at it into virtual Ethernet interfaces. And PTF and Scapy are very popular in the P4 community. Some people use PyTest or even other frameworks. Then at the upper end of the speed scale, we have full line rate testing using hardware-based packet testers, where that's really the only solution to test at full speed and scale, like 32 ports at 400 gig. Now, one of the things you'll notice is that each one of these environments has its own interface or framework to control the packet generation. Scapy and PTF is one framework, but when you get to line rate testing, it usually has a proprietary vendor-specific API or GUI to control it. And then in the middle, people often use one or more servers with NIC cards, and they use a variety of different tools to generate packets in software. Sometimes there's a fan-out switch in the middle to expand the ports, and that uses yet another scripting or language environment. So you end up with really silos of code where all the scripts are different for these different cases. And we're not even talking about the QA environment. This is just a development environment. So this creates a problem. And so as a developer, I have a wish list. I want to write one script and I want to use it everywhere in development and even maybe in the QA process. I'd like to run from slow all the way up to full line rate. I'd like a model-based declarative API so that the configuration is treated like a document. That's kind of the modern way using models. I want an open standard. I want a thriving community. I'd like to be decoupled from any specific vendor. I'd like a free, pure software-based solution, but I want to be able to migrate all the way up to commercial full performance solutions without changing all of my software. And I wanted an easy on-ramp. I want to go to GitHub, click clone, and get my code immediately and start playing. So not much of a wish list, just want everything and I want it now. So we'd like to introduce Open Traffic Generator, Snappi, and Ixia-C. And we'll explain this set of solutions right now. So, like I said, we want to use model-based interface because that's the modern way where you have a declarative model. And we start with what we call the Open Traffic Generator data models, which is an open API specification available on GitHub. And that specification describes an abstract open traffic generator, which is independent of the implementation or any vendor. Using this data model, you can derive a REST interface, which is vendor neutral and platform neutral. And that interface can be used to describe an implementation or concrete open traffic generator, which you would then use to connect to your device under test. So given such a model, you can write any REST script you want to control this traffic generator, and you can use whatever language you want, whatever platform. So already you've got some independence from vendor-specific implementations. We've done one better where we've created what we call the Snappi Pythonic client library. This is a very lean and clean, model-based, object-oriented library, which makes it very easy to write scripts to control a traffic generator. Let's look at some real traffic generators. Today, we're announcing the XCSC container-based software tester. It's a packet generator written to use the DPDK library for slow to very fast performance packet testing. These engines can drive virtual Ethernet interfaces or NIC cards approaching 100 gigabits per second. This can be used to control software device under test or a real hardware device. The container has two parts, or there's two containers. One is the traffic engine itself, which you can have many of them, one per port. And the other part is the controller, which can control many engines. This is available for download today, and there's a free version. We also have a range of hardware-based testers, which can run up to full line rate, and these can also be controlled by Snappi. Now we're looking for the community to participate in defining other traffic generator adapters so that you can have software-based testers using other frameworks such as Trex or other DPDK implementations. We'd also like people who generate or make hardware-based testers to use Snappi or Open Traffic Generator as an interface. This would create an entire community ecosystem using one library. So given this set of solutions, we can see on the constellation here of speed and scale, we've got one solution, one scripting language, one open API data model to control the entire range of speed and scale. So the wish list has been answered. Now we'd like to go on to a demonstration where we actually show this in action using a PTF test, which has been modified to use the behavioral model 2 and Snappi and the XCSC traffic generator. I took a standard repo, which is available on GitHub, the P4 guide, which is very popular, and I modified one of the tests to use Snappi instead of Scapy. So I'll briefly explain the test layout. We start with the program, demo1.p4. It's a simple switch that does IP destination lookup, MAC rewrite, and port redirect or drop. We compile that to run on the BMV2 simulator. We'll spin up 8 ports, which are virtual Ethernet interfaces. And this switch will be controlled by the P4 runtime server embedded in the switch. We're going to use a PTF script, which has been modified to use Snappi instead of Scapy. And this script will use the P4 runtime library to program tables in the Dataplane, and that will execute our forwarding behavior. We're going to spin up 5 containers. 4 of them are traffic engines, and 1 is a controller. And these will be controlled by the Snappi library. This is easy to install on your machine. You just do a pip install and import the library into your script. It's as easy to get going as Scapy is. So this is our layout. And we're going to do a specific test. There's several of them in the program. This one is a 4-port mesh test. And in this test, we're going to send 12 different flows, which we define in Snappi. And these flows will create the entire matrix of port-to-port forwarding. The neat thing about Snappi and OTG is it's very easy to define flows with sophisticated capabilities like auto increment of header fields, precise scheduling. In this test, we're going to send at 50 packets per second on all 12 flows simultaneously. And this scheduler is built into the traffic engine. This scheduling is also a feature of hardware-based testers where you can do precise scheduling at very high line rates. So this is the test setup, and we'll proceed on to the demo and actually run it. So on this set of terminals, I've got the simple switch right here, which I'm going to start. In these 4 terminal windows down here, I'm monitoring all the Ethernet ports, so you can see the packet streaming by. And in this terminal, I'm going to run the test. It's going to go by pretty quickly, and then I'll review some of the results. So once this runs, I'll rewind a bit and show you what happened. You can see the packet streaming by in the VE monitors. Okay, well, our entire test ran. Let's just rewind a little bit and take a look. So up here, we loaded the P4 program into the behavioral model. Then we started configuring Snappi to set up 12 flows, and I'm just printing out some log statements to see that I did that. So each flow is from one port to another port, and we cycle through all 12 combinations. We download Snappi config to the traffic engines, and we start sending packets. Now the first test just verifies everything is dropped, so it's kind of boring. I'll just skip over it. We can see we received no traffic as expected because the P4 tables have not been programmed. This is where it gets more interesting. We actually use P4 runtime to download the flow tables to do the port-to-port forwarding based on the IP subnet. Now we're going to start all of the packet streams again. We send 255 packets to each port-to-port mesh connection. Now we're waiting for all the packets to go through. Now bear in mind, we're sending 3,000 packets here with one start command because we set up a packet sequence on each of 12 flows. We sent 255 packets and we told them to send at 50 packets per second. So that took several seconds to go through the pipeline. This is where it gets interesting. The traffic engines maintain statistics on a port basis and a flow basis. So here we can see every port sent 3 times 255 packets to all the other ports, and we received them. Down here, it's broken down into flows, and I've named these flows for ease of understanding. Each flow received 255 frames. Now this is really interesting where you can't do this in Scapy. We're actually measuring the latency of the data plane. So here we can see in nanoseconds, this is about 7 milliseconds. Some of these are even larger. The max latency may be 55 milliseconds. So we're getting performance measurement built into this framework. And finally, we go down and we measure all the, we do some assertions in the code to decide if the test has passed or failed. And here we're counting all the packets on a port basis. We're also going to measure all the packets on a flow basis. And then I wrote some code right here to actually verify that the complete IP address mesh was received. I'm able to upload all the packets that were captured by the engines, all 3,060, and dissect the packets and look at the contents and verify that the IP address mesh was actually received. So the entire test took 20 seconds, and here I'm stopping all the engines by killing the containers, and the test is over. So there's actually about 6 tests in this file that you can run all of them. The entire program here, everything is available on GitHub, and you can download and play with this and do everything I just did. So it serves as a good example for writing your own Snappi tests. So let's go back to the slide deck. And I wanted to show, here's a table, which you can pause the video and look at this at your leisure. But here's some comparisons of Scapy versus Snappi. And I'd like to emphasize the fact that Snappi allows you to set up precision scheduling of flows, which is something you can't do with Scapy. And that scales all the way to full line rate testing. So I'd like to pass the baton to my colleague Ankur, who would like to talk about the GitHub community that we've established.
Thank you, Chris. Really nice demo. Liked it a lot. So at this point, all I'd like to add is that XCSC, as well as the Open Traffic Generator data models, are all available on GitHub. There is a GitHub organization named Open Traffic Generator. You see the URL right there. You can get a lot of instructions on how to use XCSC, how to get started with it by visiting that web page. We encourage you to try it out. It is work in progress. We anticipate adding more releases, more features, bug fixes on a regular basis. And we'd like to welcome your feedback. We'd like to hear from you. Whichever form works for you, whether it is requesting feature, enhance something more added to the data models. All is welcome. We really look forward to hearing from you. Thank you all for your time.
Okay. All right. Thanks, Chris and Ankur. Really cool demo. Looks like a great tool for Dataplane developers. I have a few questions. The first one is, one of the great benefits of using P4 is that as a Dataplane developer, I'm not constrained to standard protocols, but I can define new custom ones that fit my needs. And usually one of the problems with Dataplane testing is that takes some time. Does offer any special support for custom protocols? What's your plan for that?
Ankur, you want to take that one?
Sure. So what we have in the Open Traffic Generator data models is this ability to put in a custom header, essentially your sequence of bytes anywhere in the packet before or after any other header that you'd like. And this is really a first-class citizen in the sense that all the other capabilities that you have available, like Chris described, incrementing a certain offset or whatnot, is available. Okay. At the same time, what I'd also like to emphasize is that we are constantly enhancing these data models, and we are more than happy to add new protocol headers to those data models, and more than happy to figure out a way to work with the P4 community to see if there's a way to form a pipeline between P4 and these data models. Take a P4 definition of your header and import it directly into these data models. We are happy to work on that with people who are interested.
Cool. Yeah, it looks like there might be an opportunity to perhaps write some compiler backend or something like that.
Absolutely.
For program and spits out some data models. Yeah, that will be really cool. One last question. I saw in the demo that you guys are able to measure the latency of packets. I guess in that case, is the one-way latency. How do you do that, and how precise are the measurements? Is there any difference between using XCSC or the line rate tester when it comes to precision of the measurement?
Let me bring up a backup slide that gives a little insight into how we do that instrumentation. And I'll let Ankur respond to the precision question. What we do, and this is very established technology in our hardware-based testers, and we basically emulate this in software. We insert a special sequence at the start of payload. So this doesn't affect your protocols, and usually payload is some kind of a pattern anyway when you're doing this kind of testing. And it has a unique signature that we can detect because it's a certain sequence. And then after that signature, we have a flow identifier, a sequence number, and then a timestamp. So that's how we do the detection. And this works the same in hardware and in software. And this is a well-established technique. Ankur, would you like to handle the precision question on timestamp?
Sure. So with XCSC, your precision is limited or determined more by the Linux clock that you get. So it's, running on a server, even if you run bare metal and so on, you're not going to get more than a few microseconds worth of very precise latency measurements. But the same concept applies to our hardware-based testers, which are line rate. And there our precision is as high as, I believe, 2.5 nanoseconds. So the same script you run on software XCSC or hardware, you're getting a latency in the same unit. It's just that with hardware, you're getting something that is orders of magnitude more precise.
Got it. Really cool. All right. So I'd like to thank Chris and Ankur for the time and the great demo. Thank you to the audience for watching, and make sure to check out the other content from the P4 Workshop 2021. Thanks again. Bye, Chris and Ankur.
Thanks a lot. Bye.
Thank you.